We're in chapter 8, and this is page 10, example 6. Write an equation in slope-intercept form of the line whose parametric equations are given. Well, slope-intercept form is y equals mx plus b. And if we solve the first equation, or the first equation's already solved for x, I can just go to the second one. Wherever I see a t, plug in negative 2 plus t. And I can distribute and then get my answer in slope-intercept form. Here I have 4 plus 6 minus, hold on. The first equation I could solve for t. T equals x plus 2. So if x equals negative 2 plus t, t equals x plus 2. So wherever I see a t, I can plug in x plus 2. And then I'm going to distribute. So I get 4 plus negative 3x minus 6. And if I combine like terms, I get y equals negative 3x minus 2. B, first equation, I'm going to solve for t. If I divide by 9, I get x over 9. And then I could just plug it into the bottom equation. So in these equations, first equation, that's x equals solve for t, plug into the y equals equation. So it's 4 times x over 9 plus 2. And then I get 4/9 x plus 2. That's example 6. Next, projectile motion. This is section 8.7. The path of a projectile can be modeled by the following parametric equations, which are given as here. That's if the horizontal and vertical components of v sub 0 are known. V sub 0 is the initial velocity. That is either horizontal or vertical. D sub 0 is the initial horizontal distance. T is the time. G is the acceleration due to gravity. And what we would say here is if it's feet per second squared, it is 32. If it's meters, it's 9.8. H sub 0 is the initial height. If the initial velocities are unknown, but the angles to the ground is known, we say the horizontal velocity is v sub 0 cosine of theta. And then the vertical velocity is v sub 0 sine of theta. So then the equations will become this. X equals v sub 0. I'm replacing t. It's really, instead of v sub 0, it's v sub 0 cosine of theta times t. So I'm replacing this with v sub 0. And then plus d sub 0. And then vertical velocity, it's negative 1/2 gt squared. And wherever I see a v sub 0, I'm going to plug in v sub 0 sine theta t plus h sub 0. And what I could say here is, and this typically comes from this. If here's a right triangle and this is x, y, and theta, it's from the right triangle where we get the horizontal velocity is v sub 0 cosine of theta, because cosine of theta equals x over v sub 0. And then if you cross multiply, you would get this. And sine of theta equals y over v sub 0. And if you cross multiply, you get this. Typically, our book does not deal with d sub 0, the initial horizontal distance. All right, example 10. Suppose a professional football player kicks a football with an initial velocity of 29 yards per second at an angle of 68 degrees to the horizontal. Suppose a kick returner catches the ball 5 seconds later. How far has the ball traveled horizontally, and what's the vertical height at the time? So here's how we're going to go about doing this. First of all, in these equations, if G is 32 if it's feet per second squared, 9.8 if it's meters per second squared, we have to make a conversion. If it's 29 yards per second, we need to change it to feet. So the conversion is 3 feet equals 1 yard. And if we cross out the yards, we could say it's 87 feet per second. So that is the value we're going to use for the initial velocity. It's 87. That's the initial velocity. So the horizontal equation, there's no d sub 0, so it's v sub 0 cosine of theta t equals x. So x equals 87 cosine of theta, which is 68 times 5. So if we type that in on our calculator in degree mode, we're going to get 162.95 feet. That is the horizontal distance. And for the vertical equation, we use this equation. There is no given initial height, because assume they're kicking it from the ground. There's no value. So we would just plug in, since it's feet per second squared, we're going to plug in 32. Time is 5. And then v sub 0 is 87 sine of 68 times 5. So if we type that in to our calculator, we will find the vertical height at that time. 5 seconds later, the kick returner will catch it at a height of 3.32 feet. So these are the examples on page 10 from chapter 8.